Hello, this is an overview of Learning to Rank by Will Chirciu and Amy Edwards. This is for CSC 575 from the online section. And here we go. So the problem that we had was to predict the relevance of search results from Home Depot in relation to the query that was given. We were given a training and a testing set. The training set contained attributes, product descriptions, the search query, product title, product ID, and the average relevance score. The relevance score was computed by more of a focus group that was able to take into account all of these things and photos to decide whether the search query results were relevant to the query that was entered. This is an extremely important problem, especially for online retailers, because if they are not returning relevant results for the users, people are not going to want to shop there, which will decrease their profits, and then they won't make money.
So before we dug deeper into our project, we wanted to create an inverted index for each of the document types, the product titles, descriptions, and attributes. And this benefits us because we get quick full text searches. It's just a dictionary of terms with the values as all the information we need. And I'll show you that in the next slide. And this at the cost of slow processing time with making little changes or adding documents, or in our case, changing tokenization techniques. So this is kind of a small snippet of our inverted index for product titles. So you can see the terms here and their associated IDF values and the postings, which is just the documents they appear in and their term frequencies. All right, so for the next step, we thought about how we could create our data, basically, to run the regression on. So this obviously would involve feature engineering. We have all these details, just the documents and the queries. Now, what can we use to predict the relevance for these document query pairs? Like what features, like what's important? So obviously the first step was computing the similarities. Now we worked on both cosine and Jacquard. And to get an initial regression model, we tried the basic approach of calculating similarities based on exact term matches. And this before the inverted index, just creating document query vectors. It took hours. But once using the inverted index, it took around 30 minutes max. I think 30 minutes was associated with the descriptions. But yeah, at first glance, we saw that there were just too many zero values where there shouldn't be. We went back to the original data set and saw we were getting zero similarity for document query pairs where there were high relevance. What's happening was it's not finding the exact query term in the document. So one way to solve this is to see if any related words are in the document. And that's where WordNet comes in. And WordNet returns related words with respect to a specific term that you give it. So this could be synonyms, hypernyms, and hyponyms. So our first approach, if we didn't find a match, we would try synonyms, no match in there, hypernyms, and hyponyms. And then we'd score it based on that, based on the first discovered word. And this is kind of what our final model was based on, the similarity measures in there. But our augmented approach that we implemented but didn't get to finish running because of computational time was, I guess, more of a query expansion where we tried to find all related words, synonyms, hypernyms, and hyponyms in the documents and scored it as such, further boosting the similarity between the pair.
Another one of the features we called exact phrase. Basically, if the search query exactly was in the title or the description, this feature would get a 1 in its column, and if the search query was not exactly in the title or description, it would get 0. So it was a binary feature, just determining how exact the search is. Another one was just the counts, which is the sum of the terms in the query, description, and titles. So, rain shower head, that has 3 words in it, 3 terms. Its count is 3. This is essentially the length. And then we have length ratios for the length of the title divided by the length of the query, or the length of the description divided by the length of the query. And so this shows if a title is extremely long and then a query is very short, maybe it's not as good of a match as something that's a little more balanced for the ratio. And then this is a more interesting feature. We have percentage of the query that's in the title or the description. So you take your query, it has 2 words, angle, bracket. So the title is Simpson Strong Tie 12 gauge angle. Those 2 words, only one of them appears in the title. And so that's a 50% appearance. So the 50% of the query is in the title, and then that percentage went into a vector in which we computed for all of the queries, titles, and then all of the queries with descriptions.
So after trying many different types of regression models and doing all types of hyperparameter tuning, we found our final model to just be the gradient boost with the default parameters. Had a pretty decent RMSE on our training set using 5-fold cross-validation. Had a 0.4821 RMSE. And actually this model actually turned out to be quite generalizable to the test set on Kaggle. So as you can see here, our final results, we placed 7th in Kaggle leaderboards with an RMSE of 0.48571. Wanted to work on that had potential to improve our model included word embeddings, which are just vector representation of words created from a very large corpus. We tried using this with 100-dimension vectors, but a lot of the query terms weren't in the vocabulary of the corpus. So it was just a matter of figuring out how to deal with these specific terms. Again, query expansion to augment some of our previous mentioned features, including the similarity measures. As for brand matching, we tried manually recording brand names in a text document by combing through the original training and test data. Unfortunately, we weren't able to get exact matches, maybe due to misspellings or spacing issues. So we had a lot of zeros, which wouldn't help our model, which wouldn't be a significant feature, really. So just further improving this algorithm. And again, it'd be really nice if we had more computing power. My computer took hours to run some of these algorithms. So just need more RAM, more memory. I know we had some memory issues as well. So either that or just using a distributed system to compute some of these would really help in the long run. Be able to fine-tune things without having to wait hours to see if it improved your results. Anyway, that's all we have for you guys. Thank you so much for your time.